Change, change, change. 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 Change, change of food.
Hey Ramblers, this video is going to cover chapter 3.4 in our textbook, and we'll deal with the chain rule. Now the chain rule is the rule for differentiation, the shortcut you will, for differentiating composite functions. So in this video we're going to explain or just review what composite functions are, and then I'll introduce to you the chain rule and how we use it to differentiate composite functions. Then we'll take a look at a couple of examples and wrap up the video. So please take careful notes, make sure that you're practicing along with the examples, and I hope this helps. Thanks for watching. You may remember from the first quarter in chapter 1, we talked about composite functions. That was when we had an outside function, f of x, and a function inside of it, like g of x. And we called g of x the inside function, and f of x was the outside function. And really, an example might help most of all. Suppose we had the function x squared plus 1, something we're all very familiar with now. But then imagine that that was put into another function. Say it was raised to the 100th power. So this would be an example of an outside function, f of x, and then an inside function, x squared plus 1. So let's take a look at what's going on and why we call one an inside function, one an outside function. Well, suppose you're given an x. That x is taken and it goes into, if we were to use the old function machine example, that goes into g of x. And when it comes out of g, it's no longer x, so it's been acted upon. So we have to take that change into account. Well, so what comes out is g of x. And when that is put into the f function, another change occurs, and out comes a second output called f of g of x. Now, composite functions can have many functions, as we'll see in one of the examples. But it's most important that you recognize composite functions when you see them so that you can use the chain rule. Okay, now let's look at what the chain rule tells us to do. The chain rule is not very difficult to memorize. It's just important to learn how to use it and to recognize when to use it. So the chain rule is stated as this: that if we are given an inside function, g of x, and that is inside another function, f of x, and we want to take the derivative, there's kind of a multi-step formula. The first thing is that we take the derivative of the outside function, f of x, and so that becomes f prime of x. And notice we don't change the inside function. Then we multiply by the derivative of the inside function. Okay, an example here would really help. So let's go back to the example that we were looking at. Suppose we said that we had f of g of x, and that equaled, I think we said, x squared plus 1 to the 100th power. So what would the derivative look like? Well, according to the chain rule, we would take the derivative of the outside function. So that would be 100 times the inside function to the 99th power. Now what is the inside function? Well, that's x squared plus 1. So that satisfies the first part of the chain rule. But now we have to multiply by the derivative of that inside function, which is just 2x. And that's all you need to do. You're done. Okay, let's take a look at a couple more examples, and then we'll wrap up. Okay, let's try and find the derivative of the square root of 5x plus 2. All right, well, recognizing that our inside function is 5x plus 2, and we have a square root of that, we have to take the chain rule. Now, I always think it's a good idea to rewrite radicals as fractional exponents when you're differentiating, because that reminds you to use the power rule properly, and it also helps with the chain rule. Okay, so if we're going to take the derivative of this, we're going to get the derivative of the outside is 1/2 times the inside, which is 5x plus 2, and then that's going to be to the negative 1/2 power, because we have to use the power rule, and so that exponent gets decreased by 1. But now we have to multiply by the derivative of the inside function, which is just going to be 5. So our final answer would be 5/2 over the square root of 5x plus 2, if you're going to have it perfectly simplified. Okay, Ramblers, I want you to try the next one on Zaption, so give this a shot. Let's take the derivative of e to the x squared plus 10x. Take a minute, pause it, well, you'll have to because the Zaption will pause it for you, but try to imagine or think about what is the inside function here and what's the outside function. Okay, so if we take the derivative, the outside function is e. So since that's its own derivative, nothing changes. We just get e to the x squared plus 10x. But now we have to multiply by the derivative of the inside function, which is the exponent. That's just going to be 2x plus 10. So that's your answer. Okay, let's try another one. How about d dx of 3x to the 5th plus 2x, and that whole thing is going to be to the 4th power. Okay, we're going to take the derivative of the outside, which will be 4 times the inside, and to the 3rd power, since we're using the power rule. So remember, with the chain rule, the inside doesn't change at first. So once we've taken the derivative of the outside, now you multiply by the derivative of that inside function, and you get 15x to the 4th plus 2. Okay, let's try one more, and this one's pretty complicated, so don't worry if you don't get it, but I want to show you that sometimes we have multiple uses of the chain rule. Okay, look at this scary thing. We're going to use the chain rule a total of 4 times here, and I want you to do it on your own in Zaption and then compare it to the answer. But be careful that you are rewrite this expression using fractional exponents. I think that's a big step in doing any kind of differentiating right, but especially when working with a chain rule. Okay, good luck. All right, so I'm going to rewrite this as 1 plus e to the 3 plus x squared to the 1/2, and that whole thing is to the 1/2. So now if I take the derivative of that, well, I guess I should have said this is equal to the derivative of that. That's going to equal 1/2, because that's the derivative of the outermost function, and that's going to be taken to the negative 1/2. Now I don't change the inside function. That still remains 1 plus e to the 3 plus x squared to the 1/2. Now I multiply by the derivative of the inside function. But you'll notice this inside function is also a composite function. So we're going to have to use the chain rule again. So I'll have 1 plus e to the square root of 3 plus x squared. Now why am I getting the same thing? It's because this inside function is really a function of e, and that is its own derivative. So now I'm ready to take the derivative of this inside function, which will be 1/2 3 plus x squared to the negative 1/2, and I will multiply by the innermost function, which is 2x. Okay, sorry to use different colors here, but all of this is on the same line, I mean, even though this is a derivative of an exponent, it still remains on the same line. So this thing will simplify kind of like this. So if it's all written on the same line, it looks like that. And then, of course, this 2 and the 2x and that one of the 1/2 canceled out. So that's why I'm left with just an f at the end. Okay, you could go on to simplify this some more by putting this expression down the denominator because of that negative exponent. And then this would also be a negative exponent, so maybe that will go in the denominator too. But the chain rule, something as complicated as this, we won't need to worry about until we've had a little more practice. Okay, Ramblers, thanks for watching, and I'll wrap up. Okay, Ramblers, so that was the chain rule. And you can see that it's not really that hard to memorize. It's not like, the quotient rule, but it's really important to know when to use it. So we have to pay careful attention to composite functions, recognizing functions inside other functions. Hopefully they won't get as complicated as that last example where we had to use it 4 times. That really is pretty extreme. But you want to make sure that you have this memorized, and be careful to note that the first time you take the derivative of the outside, the inside doesn't change. It's not till you multiply the inside, the derivative of the inside, after you've taken the derivative of the outside and left the inside alone. Okay, so that takes some practice. We'll get plenty of that. So hope you took good notes. Hope this made a little sense, and thanks for watching.
Chains, my baby's got me locked up in chains.